Hey, today we're going to look at how do we simplify square roots, which is basically just how do we get the square root of 8 to be 2 square roots of 2. So I'm going to show you how to do that today. So let me just erase this real quick. All right. The first things that we need to know are the product property and the quotient property. The product property says that the square root of a times b is equal to the square root of a times the square root of b. All right, so we're going to use that a lot today. We can also use that the square root of a over b for the quotient property is the square root of a divided by the square root of b. The way that you may have seen this before would have been factor trees. For example, if you were trying to find the square root of 8, right, you might have had to find all the factors of 8 and get them down to the primes. And anything that doubled up, that came outside of the square root. And that's where we have this just becomes a 2, and then I'm left with a square root of 2 inside. But we're going to simply just look for the factors that are perfect squares that we can pull out of these radicals, just by listing all the factors ahead of time. So let's look at an example of that together. Let's consider the square root of 18. What are the factors of 18? The factors are 1 and 18, 2 and 9, 3 and 6, right? And so I look for a perfect square. I know 9 is a perfect square, right? So I'm going to use 2 times 9. So here I'm using the product rule. I know that the square root of 18 is equal to the square root of 9 times the square root of 2. Well, I know the square root of 9 because it's a perfect square. So this is equal to 3 times the square root of 2. So let's try that one more time with, say, the square root of 80. All right, so I'm going to list out the factors of 80. It would be 1 and 80, 2 and 40, 4 and 20, 5 and 16, 10 and 8. Do I have a perfect square anywhere inside? Yeah, right here with this 16. So this is equal to the square root of 16 times the square root of 5, right? Because these things are 5 times 16 is 80. Square root of 16 is 4, and we have times the square root of 5 left over. So both of these are using the product rule. Just to show you the quotient rule, if you had the square root of 2 over 25, remember that this is the same thing as square root of 2 over the square root of 25. And you should know the square root of 25. That's just 5. And the square root of 2 can't be reduced anymore. So square root of 2 over 25 simplifies to the square root of 2 over 5. Go ahead and try to simplify these two square roots. 5 times the square root of 117 and the square root of 4 over 9. So go ahead and pause the video. All right, well, 117 didn't have a whole lot of factors, and so I look for the biggest perfect square inside. I have this 9. So I have 5 times the square root of 9 times the square root of 13. The square root of 9 is 3, so now I have 5 times 3 times the square root of 13, and we can combine these things. This would be 15 square roots of 13. And then the square root of 4 over 9 is the same thing as the square root of 4 divided by the square root of 9. And this simplifies to 2 over 3. At this point, I'd like to point out that so far we haven't simplified and left a square root in the denominator. If that does occur, then we have to rationalize the denominator. Take a second to copy down this chart of how we rationalize the denominator, and then I'll talk about it in just a moment. All right, so I'd quickly like to talk about why each of these things works. First, this square root of b. If I had, and that's in the denominator, if I had like 1 over the square root of 3, if I multiply by the square root of 3 over the square root of 3, because that's what it tells me to do, multiply the numerator and the denominator by whatever's in the denominator. Well, 1 times the square root of 3 is the square root of 3, and then the square root of 3 times the square root of 3 is the square root of 9, right? And what's the square root of 9? 3. So anytime that you have a square root multiplied by itself, the square root just comes off and you have whatever was inside. And then I hope you noticed with these bottom two versions, you have this a plus b, well then you have to do minus, or the minus you have to do plus. These are called conjugates, and anytime that you have a plus or minus, you have to multiply by the opposite in order to make the square root go away. Okay, if you don't multiply by the conjugate, you're still going to have a radical somewhere in your expression. So let's just jump into a couple of examples, because I think that's the best way to see this. And actually, just before we do, oh, here, I'll just change the colors around. Let's just quickly review. Square root of 2 times the square root of 2, well, that's 2. Square root of 5 times the square root of 5, that's 5. Right, any square root multiplied by itself, you're just going to get that number back, right? Because this is square root of 4, which is 2. This is square root of 25, which is 5. So it's just good to really have that down. All right, so let's look in that at a couple of examples from the first case. Here I can break the square root of 5 over 2 into the square root of 5 over the square root of 2. All right, now I've got a radical in the denominator, so I'm going to have to rationalize it. Since there's no plus or minus, I don't have to multiply by the conjugate. I just multiply by whatever's in the denominator. And I have to do the numerator and the denominator because you're basically just multiplying by 1, right? So you're not changing anything. Square root of 5 times square root of 2 is square root of 10. Square root of 2 times square root of 2, it's 2. Do any perfect squares go into the square root of 10? Well, the factors are 1 and 10, 2 and 5. So no perfect squares. This is simplified. Here in the second example, I've got this plus, but I don't have to worry about it because it's not in the denominator. So all I have to multiply by is the square root of 2 over the square root of 2. Now, this is a binomial, so I'm going to have to multiply the square root of 2 times both of these things. So I have 3 square roots of 2 plus square root of 3 times square root of 2 all over 2. Now, square root of 3 times square root of 2, that's the square root of 6. So I have plus square root of 6 over 2. In this case, the square root of 6 has no perfect squares inside of it. Now, if you wanted to divide everything by 2, which in this case we can't, you have to check for the number outside of the radical. All right, this square root of 6 is not divisible by 2 because this represents a whole different number. The square root of 6 is like 2.449489. So be careful with that. But in this case, this is as far as we can go. All right, so this time let's try 3 over 7 plus the square root of 2. Okay, now it's of that other form, so I have to multiply by the conjugate. I'm going to multiply by 7 minus the square root of 2 over 7 minus the square root of 2. So in the numerator, we have 3 times 7 is 21 minus 3 square roots of 2. And in the denominator, notice, again, this is just difference of 2 squares. So when we think about it like that, like difference of 2 squares, that's just 7 squared minus the square root of 2 squared. So we have 49 minus the square root of 2 squared is 2. So here we have 21 minus 3 square roots of 2 all over 47. These aren't all divisible by any number, so this is as far as I can go. All right, for our last example, let's try 3 plus the square root of 3 over 4 minus the square root of 2. So I'm going to multiply by 4 plus the square root of 2. Okay? In the numerator, we're going to have to FOIL these. Right? So whenever we FOIL, we have 3 times 4 is 12 plus 3 square roots of 2 plus 4 square roots of 3 plus square root of 3 times square root of 2 is the square root of 6. all over 4 squared, 16, minus the square root of 2 squared, 2. Okay, now I'm going to rewrite all this. I've got 12 plus 3 square roots of 2 plus 4 square roots of 3 plus the square root of 6 all over 14. And we can rewrite this in a lot of different ways. If you wanted to write each of these over the denominator, you could do that, and you could simplify a little bit further this way. But because of the square root of 6 not having anything in front of the radical, I can just say, all right, we're simplified right here. All right, and that's simplifying square roots.